All right, well, today we're going to kind of go into a brand new field of mathematics. Earlier in the year, I introduced you to this idea of radians, which was a new way of defining something that you had worked on in a different way. And we're going to do something similar today, where we're going to rework our way through something that is, in fact, describing something you've done in a similar fashion, but we're going to redefine that. So imagine, if you will, that there was a coordinate system and you had an object located to the right 3 and up 4 from where you were. You can kind of picture that like you're standing on a grid and there's a race to get there. Now, if I said it was over 3 and up 4, of course, you guys all know that you could move to the right 3 on that x-axis, stop, turn to the left, and run up 4 units on that y-axis, and you could grab the prize. But you, meanwhile, have lost because you went over 3 and up 4, meaning you actually moved a total of 7 spaces, and your friend just went ahead and pivoted a little bit and turned directly towards the object and ran forward 5 units, and they grabbed the flag, and you are 2 steps behind at least. So obviously that would not be the efficient way to move right 3 and up 4. Maybe just going directly towards that path would be more efficient, which if you think about, there's all sorts of things that are that way. You know, the military, if they're going to send a rocket and destroy a target, they wouldn't tell it the missile to move west 400 miles, come to a screeching halt over Kansas somewhere, and then turn north and go somewhere else. They would actually point it directly towards where they want to go and tell it a distance to go. And that's a new version of mathematics that is known as polar. So we're going to go ahead and take a look at what happens if we go ahead and move into this new idea that is called polar. And I believe I have not activated my ImageMate, so I need to do that. So let's see if we can share that ImageMate here. Let's see, why is this not sharing? Share, is my ImageMate there? I believe that it is. So let's double check this. I've had some issues with this before. So let's just double check this one more time. My apologies for pausing the video for a second, but I don't want to have to recreate this entire thing. So yeah, it's working correctly this time. So anyway, this is the system that you have been used to throughout your time in school. This is called the Cartesian coordinate system, and this is the kind of paper that we're going to use for the other. So imagine if someone handed you x, y being 5, comma, negative 5, which tells you to move over 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. This coordinate right here, we'll call that A, to the right 5 and down 5. This is called the Cartesian coordinate system. Now, if we wanted to get there more rapidly, what we could choose to do is we could figure out a little bit of data. Now, of course, it went to the right 5 and down 5, why I made that negative. Of course, based on the simple Pythagorean theorem, that would make this radius from here to here 5 roots of 2. So that would tell you exactly how far to go. And the angle could be found very quickly because, of course, I handed you, for convenience sake, an isosceles right triangle. So I told you to rotate this way exactly 45 degrees, or pi over 4. And in fact, we know from our previous units that that would be a negative angle. So in this paper right here, what we have is this stuff is drawn as follows. This would be 0, this would be pi over 2, pi, 3 pi over 2, etc. And so if I were to rotate down pi over 4, that would be right here, and I would go out to 5 square roots of 2. And on my calculator, 5 square roots of 2 is approximately 7, just a little bit over 7. So I'd come down to this angle negative pi over 4 right down here. And I would go out 1, 2, 3, 4, 5, 6, 7. So just a tiny, tiny bit more than that. And that's a new representation of that same value. And the way we do that, in rectangular, we write x, comma, y. And in polar, we write r, comma, theta. the radius that you went out, which we said was 5 roots of 2, or 7.07, and theta would be negative pi over 4. But somebody else might have said, no, 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 I don't really like that particular representation, 5 roots of 2 comma negative pi over 4. I actually thought, instead of rotating down, I thought about rotating around the circle. So could we equivalently say that that was 5 root 2 at 7 pi over 4? And in fact, that is also an equivalent statement, which leads us to a fact that's actually kind of interesting. In the rectangular system, every coordinate is unique. There's literally one representation for every point in space. And in this particular story up here in polar, we could actually represent every single coordinate in an infinite number of ways. We could rotate forward, we could rotate backwards. In fact, somebody else might have spun around the circle multiple times and come up with another representation of this angle. And you'll see a few more of those as this particular video proceeds. So now that would help us to talk a little bit about how this plays out. So if you were looking at the Cartesian coordinate system and I gave you a coordinate x comma y, you would know that you would go forward x, you would go up y, and x and y in this case are variables, meaning they could literally be positive, they might be negative. I just did it for convenience sake in the first quadrant, but it would be equivalent. Now we would know by the Pythagorean theorem that x squared plus y squared would be r squared, and then if I took the square root of that, I would get r. So that's how we're going to say that. This would be theta. And so what we could also say is that the tangent inverse of y over x. Now, you want to remember that normally in trig, I would give you the angle and you would tell me the ratio. In this case, I'm giving the ratio to find the angle. Now, this does violate a little bit of an idea that's going on because the inverse has to be 1-to-1. That was that tough concept that we went over, meaning there's literally only one answer. But you can see right here, we had more than one answers, which is why I kind of say sort of when I write this. This formula will tell me one of the answers, but it won't tell me all of the answers. And sometimes it may not give you the representation that you were specifically hoping for, but it will give you a valid representation of that answer, but not all of them. So you'll notice that in this case, I gave you x and y to get r, I gave you x and y to get theta. So these are the two equations that help us go from rectangular x and y over into r and theta. And in a similar way, if we went back to basic trigonometry, SOHCAHTOA, sine is the opposite over hypotenuse, I would know that the sine of theta would be y over r, which is interesting because I've got theta, which is a polar idea, y, which is a rectangular idea, and r, which is, oh, that's a polar idea. But if I cross multiplied, remember this is 1, so r sine theta is y, all of a sudden, this is a polar, this is a rectangular, so if I knew r and theta, I could plug in r, I could plug in theta, and I could find out what y is. And in the same way, the cosine of theta would be adjacent over hypotenuse, SOHCAHTOA, x over r, so r cosine theta is x. And lo and behold, there we have it. This is how you take x and y and get r, y and x to get theta. In other words, going from rectangular to polar. But if I have the polar coordinates, r theta, and I want to go to x, y, I have a simple little formula that can help me get there. So with that in mind, I'm going to go ahead and take a look at a couple of quick examples on how we can play our way through this. So in this particular story, this says, let's plot the following and rename them in a different way. And so we're going to plot, these are all polar coordinates, and you do have to know that they're polar because literally you could go to the right 6 and up 11 pi over 6 and get some weird coordinate, but these are all given in polar. So this is telling you to rotate to the point 11 pi over 6. Now, we do have to learn how to use this graph paper a little bit. we know that this is 0 radians and pi over 2 radians, but that would mean that this is pi over 4. And if you kind of count the number of these radial arms that go out, you would see there's 1, 2, 3, 4, 5, 6 spaces in here. So every one of these spaces is pi over 12. So that's 1 pi over 12. This one is 2 pi over 12. This one was 3 pi over 12, 4 pi over 12, and 5 pi over 12. And of course, 6 pi over 12. So you can kind of see how that plays together. So if I told someone to rotate to 11 pi over 6, that would be all the way around to here. That's 11 pi over 6. And it tells me to rotate to the 6th circle. So 1, 2, 3, 4, 5, 6. So there's my point A. A is the 6th circle out at the angle 11 pi over 6. That 11 does not look very good now. That's 11 pi over 6. Now this one tells me, let's go out to the 3rd circle, 1, 2, 3, but it tells me to rotate backwards 5 pi over 4. So of course this would be 4 pi over 4, rotating this way, 4 pi over 4, so one more would be here. So this radial arm would be, you could call that 3 pi over 4, but equivalently you could call it negative 5 pi over 4. So 1, 2, 3, that would be right here. So point B would be backwards 5 pi over 4 on the 3rd radius. I will frequently mess this up because notice that I actually went to theta first and I went to the circle second. I do that. I wish we wrote theta first and r second, but we don't get to make the rules. The person who first comes up with this method is the one that gets to do that. So of course, one thing that I did for convenience sake is I made this graph paper with precisely 10 circles. So 10 at pi would be right here because I went to the 10th circle and pi is straightforward. Now, this is the first one I'm going to hit you with something kind of new. This says go to the angle 5 pi over 3, which is right here. But notice as I'm facing 5 pi over 3, this silly thing tells me to go backwards 8 units. So that's going to come backwards this way to the 8th circle. So that's kind of strange. I'm pointing to 5 pi over 3, which should be down here, but it tells me to go backwards to the 8th circle right there. And in a similar way, I'll just look at this one right here. This tells me to go backwards 3 pi over 2, which would be up here. Notice I rotated backwards 3 pi over 2. That would be facing up, but it tells me to go down 10 spaces. And again, for convenience, I made it 10 circles, so it's easy. If you really wanted to see point E, that would tell me to rotate to negative 5 pi over 6 and go backwards to the 7th. So it would be in here on the 10, 9, 8, 7, right here. So notice I went backwards 5 pi over 6, which would have been right in here somewhere, but instead I went backwards to point E. Now, all of these, I gave you a name and asked for the location. Over here, I gave you a location and I asked for a name. And I did mention that earlier that there's more than one way to name each. And so I'm not going to do all of these points. I just thought I would do a couple. So when I look at A, I notice that this would be 12 pi over 12 if I rotated all the way to the negative side of the x-axis. So this is going to be the radial arm 11 pi over 12. It's clearly all the way out at the 10th circle because it's right at the edge, so I could write r and theta. But if I wanted to, I could have told somebody instead to rotate down pi over 12, which would be down here somewhere, and rotate backwards 10 units. Now again, those are two representations, but there are many, many, many representations that are out there. I'm just choosing to do a couple. For part B, it looks like we are sitting at angle 0 and we've gone out 1, 2, 3, 4 radii. But of course, somebody else might have said, hey, you know what? I want you to rotate 2 pi, which is a full circle, and go out 4. Or even though it says name it in 2 ways, I could do many, many, many. What if I rotated to pi and I'm facing this way? Where would I have to go? Right, you'd have to go backwards 4. Now, in that same way, I'm just going to skip down to letter F right here because I only want to do so many of these problems. Keep the video a little bit short. But this is some kind of a pi over 4 angle that you could see. And I have rotated down pi over 4. I'm on the 10th circle, just so we didn't have to count live on this video quite so many times. I use the number 10s and 9s a lot. So that would be 10 at negative pi over 4, or equivalently, I could have rotated to 7 pi over 4 and gone forward 10, or I could have rotated into the second quadrant over here at 3 pi over 4 and chosen to go backwards 10. There's all of these different ways that we could represent this, and that's just ways to actually plot points and understand what points are in polar. I hope that that was helpful, and I hope to let's stop this share, and I hope to see you soon. Please stay in touch. If you have any questions, let me know how you're doing. Hope you'll have a great day.